In this example, we'll use local linear approximations. We'll do another local linear approximation, but what we'll do is we'll derive a general formula for local linear approximations. This formula is something that you should see because it's a formula that will be refined in Calculus 2 to give even more accurate results. But I'll be honest with you, I really feel like students you should go back to just finding the equation of the tangent line and evaluating that. That's something that you'll remember to do. The formula you'll tend to forget, and I think it's important to remember the mathematics that we're doing, not just remember them for an exam here. Okay, so let's suppose that we know the value of f at x0 and the value of its derivative f prime at x0. And what we'd like to do is we'd like to estimate the value of f at x0 plus some delta x, where we'll assume delta x is small, so x0 plus delta x is close to x0. It's just changed it by just a little bit. Now remember that the point on the graph of y equals f of x will be x0 plus delta x, and the y-coordinate will be f of x0 plus delta x because it's on the graph. And what we're going to do is we'll have a point on the tangent line at x0 plus delta x, and then I'll just say y sub tangent line, the point on the y-coordinate on the tangent line. And this y-coordinate on the tangent line will be approximately the y-coordinate on the graph, and that's how we make our estimate. We use the y-coordinate on the tangent line rather than the y-coordinate on the graph. So let's see how this would work. All right. So first of all, let's come up with the equation of the tangent line. We'll start at the values of for which we know the function and its derivative. We know those, say, at x0. So we know at that point, then the y-coordinate at that point is f of x0, and the slope at that point is f prime of x0. Now from this we can write the equation of the tangent line. We'd have y minus, and I'll just y minus the y-coordinate, which is f of x0, is equal to the slope f prime evaluated at x0 times x minus the x-coordinate, which was x0. And I can add f of x0 to both sides. And I'd have y is equal to f of x0 plus f prime of x0 minus of f prime of x0 times x minus x0. All right, now let's make our estimate. We know that this f of x0 plus delta x is approximately the y-coordinate on the tangent line which would be given by this expression where the x is replaced by x0 plus delta x. So notice that this f of x0 plus delta x is approximately equal to this expression, and that expression, well, we can write as f of x0 plus f prime at x0 times x plus x0 plus delta x minus x0, which is just delta x. And this is our estimating formula. All right, so I guess I don't have to worry about the point on the tangent line. And I've derived all of that here. Okay, again, just in general. Now let's use this to estimate the cube root of 65. So if we're estimating the cube root of 65, all right, here's the way we would do that. Well, f of x, what operation is being performed on 65? Well, it's the cube root of x. So our f of x is the cube root of x, which would be 1/3 x to the negative 2/3. Okay, I'm sorry, which would be, I took a derivative, I wasn't thinking here, x to the 1/3. Then the derivative would be 1/3 x to the negative 2/3, or 1/3 times the cube root of x squared, x to the negative 2/3. Okay, let's let our x0 be a place where we know the values of f and f prime, and that would be a nearby value where that would be, you would like it as close as possible, which would be 64. I know the cube root of 64, and I'll need that to evaluate either of these. Our x0 plus delta x is the value at which I'd like to estimate this. That would be 65. Well, if x0 is 64 and x0 plus delta x is 65, that means that delta x must be 1. So our estimating formula, f is f of x0 plus delta x is approximately f of x0 plus f prime of x0 times delta x. And that would be f is the cube root of x0 plus delta x is 64 plus 165 is approximately, f is the cube root of x, and x0 is 64, plus f prime 1/3 times the cube root of x squared, that would be of 64 squared, times delta x, which is 1. This would be, well, the cube root of 64 is 4. 4 cubed is 64. Plus, and then a way to evaluate this a little more conveniently is this is 3 times, and we could write this as the cube root of 64 squared. Okay, instead of squaring 64, then taking the cube root, we could take the cube root and then square it, and multiplying times 1 is just that. So this is going to be 4 plus 1/3 times, well, the cube root of 64 is 4, and when I square it, I'll get 16, so 3 times 16, that would be 4 plus 1/48. 4 plus 1/48. And if I look at 4 plus 1/48 on my calculator, that's going to be 4.02083, and the 3 will repeat. So that's what that value is. Let's compare this with the actual value. I have that down below here. All right, if I look at that, there we have that. The actual value is 4.0207. All right, and so we're about off in the 10,000ths, place by about 1. So off by about 1/10,000. So again, a pretty good estimate. Okay, but again, we can use this formula. I should add that this formula, f of x0 plus delta x, is approximately f evaluated at x0 plus f prime evaluated at x0 times delta x. We could add to this to make this a little more accurate, and you'll see how this works in Calculus 2. If you wanted a more accurate estimation, all right, well, we start the same way. And then we add to that another term, f double prime, second derivative at x0, divided by 2 factorial, which is just 2 times 1, times x, or delta x squared. And then we could add to that f triple prime, the third derivative at x0, divided by 3 factorial, which is 3 times 2 times 1, all right, times delta x to the third. I hope you see the pattern here. Plus, we could keep on going like that to however much accuracy we liked. And you'll see that in Calculus 2, but I'll just point that out now. Okay, there's, again, a local linear approximation using the formula.